Okay, recorded. Okay, continue.
Lepas tu kan dia makan dalam kan doktor.
Hmm.
Jadi saya rasa ni 100. Jadi dapat bahagian ni.
Okay, alright. So isotropic makan on the side lah. Okay, thank you, Amirul. So so you add on to the first point. Okay, edge sides. Saya tambah edge side lah as the summary. Edge sides. Right. Any other? You can elaborate on this point, or you can add on a new point. Anyone else? Akilah, anything, Akilah? Any suggestions, Akilah? You can unmute yourself. Ada ke, Akilah? Anything? Arisha. Arisha, how about you? Arisha, any any ideas? Senyap je ni. Huda, ada Huda. Arisha, yes, go ahead. Arisha ke? Ya, Arisha. Saya dengar putus-putus lah, Arisha. Arisha ke? Yang lain boleh dengar ke saya je tak dengar? Just checking. Saya dengar putus-putus. Okay, right. Betul-betul. Okay, it's okay, Arisha. You can write down, it's okay. You can write down, nanti saya baca. Saya dengar putus-putus. Arisha, saya tak dengar, Arisha. Saya dengar putus-putus.
Saya
Saya Arisha
macam sama dengan Miro. Doktor tak dengar saya ke?
Okay, sama dengan Mirul. Okay,
Hello?
right. Okay, thank you. Ya, saya dengar. Ya, silakan.
Hello?
Ya, saya dengar. Dengar. Setuju dengan Mirul. Okay, Arisha, thank you. Ya, yang ni siapa ni? Yang ni Arisha juga ke? Right, it's okay. Huda, how about you, Huda? Ataupun anybody else yang ada other ideas or you want to add on the first point? Tak ada. How about Kali, anything Kali? Any suggestions, Kali? Kali ada? Juaria, any idea Juaria? By the way, okay, while waiting for your responses, selalunya, okay, Juaria, I found some research paper actually. Okay, right. Nanti kalau you ni, you can just share, in the chat box. Selalunya bila you kerja nanti in the internship and in the real job, selalunya kalau you ada issue, for example, you have something, something to solve defects or CD or standing wave or resist coming or underdeveloped, overdeveloped alignment, over edge, scrap, blah blah. So there'll be occasionally short discussion. Macam you ada satu team tu ada certain layer. For example, if you're in charge of polysilicon punya printing, polysilicon punya lithography. Polysilicon punya lithography. So there'll be issues like poly broken or pattern collapse or CD over underdeveloped, DI, FI, CD bias, and many others. Okay, so there'll be occasionally short discussion. Maksudnya you punya team leader akan panggil masuk meeting room, discuss for like 20 minutes how to solve, what are the possible root causes, what are potential issues, starting from defining the problem. Define problem is the first one. And potential root cause and how do you solve, how do you prevent. There'll occasionally be short discussion. So the team will be pulled into the meeting room for like 15-20 minutes, discuss bam apa benda yang point yang you nak buat, yang nak solve, then go to the fab and solve. Okay, so these are among the situations, if you like, the situation of the culture that you will see during your internship and during your work later on. Okay, the issue, discuss 15-20 minutes, and then go and do your work, collect data, present, and try to see if you can actually solve the issues. Okay, so this is one of the situation. Okay, any other? Sebelum saya share jawapan, ada few options that you can do to be able to realize this, but I'll just wait for the last one. Then I'll share the answer, and then we will move on to diffusion. Any other opinions? Alia? Anything, Alia? What do you think? Any suggestions? Okay. Ada? No? Plasma trimming process. Ah, interesting. How's it, Alia? What do you mean by trimming process? Can you unmute yourself and explain a little bit on the trimming? Sounds feasible. All right, let me read this. Hold on. This is by Alia. Okay. The most common method of CD reduction is plasma trimming, in which the photoresist or the resist and underlying pattern layers are etched in semi-isotropic fashion to reduce the dimension prior to applying an isotropic. All right, this is brilliant. The chemistry used for these types of processes includes oxygen mixed with chlorine and another halogen to modulate the trim rate. Okay, trimming, trim dia kecilkan ni lah, kecilkan CD. And anisotropy. The obvious drawback to this approach is that the mass height is reduced, right? The mass height is reduced, so that means the resist height and the whole thing is reduced by the trimming process, leaving less mass for the substrate etch steps. Right, the line edge or line width roughness, LER, LWR, from the photoresist may be reduced somewhat by the trimming process, but pattern distortion often occurs near turns or bends in the pattern of fine features due to stresses within the film. Ni artikel saya jumpa. Right, this is interesting. Close to the answer that I'm sharing. Okay, plasma trimming, brilliant. Thanks. So ni dari mana, Alia? Is it from a journal paper or something? Oh, article. Okay, article. Right, thanks. So Juaria, is it close to the answer above yours from Brewer Science? Saya tak tengok lagi dia punya link tu. Is it close? Ah, maybe, right. Okay. So plasma trimming, So plasma trimming is called here semi-isotropic. So that's pretty close to what Faris and Amirul mentioned. Okay, and you agreed previously. Semi-isotropic. Mana dia isotropic, but then you have a bit of anisotropy in the etch, okay, in the etching. Right, interesting. Thank you very much. So let me just share the answer, and this is not the only answer, right? Okay. You can also have a look at Saya share ni dulu, saya beritahu some other options. Right, so let's have a look. Okay, can you see the screen? Bagus screen, my PDF. Cool. Right, answer. Ini soalan exam. So see 30 marks. So in this case, the dimension is different, 500 to 200, but here we're talking about 200 to 100. But the essence is still the same, right? So you want to reduce the CD. So just like what Alia mentioned in the comment, you want to reduce the CD, but it will eat the height of the structure as well. And dia akan ada other side effects lah, macam LER, NLER, all the stuff. But that's all right. Let's just understand the essence of this. So what you can do is you have your resist there. The white area is the resist. Okay. So untuk jawapan ni, I want to trim from 500 to 200. So let's just imagine this 200 kat sini ni is actually 100 lah. So 200 here belongs to 100 in this particular example, in our example. Boleh naik gambar dinding ni. Camera. Okay. Right. So you have pattern down to 200. Sorry, let me just get this correct so supaya you tak confused. So assuming the 200 in our example is 500 now in this answer, and assuming your final CD of 100 is 200 in this example. So saya akan tunjuk example 500 to 200 while we are trying to understand 200 to 100. Very same thing. Cuma different dimension je, tukar number je. Tapi sama je. So you need to print 500. So that means your system is capable of 500, but you want to trim it down to 200. So you tengok kat sini, bila you nak trim it down to 200, the height will be reduced and the width will be reduced as well, just like what Alia mentioned, the CD reduction. So this can be done by using isotropic RIE or semi-isotropic as the explanation in the chat box. Oxygen plasma to etch the resist. Remember, etching the resist or etching we discussed yesterday is isotropic in nature. So that can be done in order to scale the whole thing. Maknanya you print feature besar ni, when you etch, dia akan jadi kecil, dia akan jadi rendah dan lagi narrow. So that brings you down to around 100 nanometer that you have to control. Then remember you want to pattern the polysilicon as the gate. So eventually resist tak akan ada on the structure. You will be left with polysilicon as the gate, sitting on gate oxide, sitting on silicon. So kita punya gate tu yang akan control. If you imagine this is to fabricate MOSFET, then your gate, the V, you punya gate voltage itu akan apply on the polysilicon. Resist is out of the equation because it's just an intermediate step to enable the patterning, but it's not there forever, okay? So the moment you have scaled it down to about 200 in this case, or 100 in our example, then you can use anisotropic RIE or ion milling, vertically unidirectional, in order to trim on the side, so that you eventually end up with 100 nanometer. So then the resist will be left on the polysilicon like this, like in the second step, and the gate oxide and the substrate remains the same. Okay, and then the moment you have tuned your CD to the intended CD, which is 100 in our example and 200 in this particular case, this particular answer, so you can then remove the resist and you will be left with 100 nanometer or 200 in this case of polysilicon on the gate on the silicon. Okay, so is it clear? So it's a combination of isotropic RIE or something like etching to remove to scale down the resist isotropically, or you can also say semi-isotropically depending on the elaboration. And then you trim the CD with a directional RIE and isotropic etching, and then eventually remove the resist in order to leave polysilicon gate on the gate oxide on the silicon. So there you have this. Okay, they have this Raja 4 ni kat atas ni. right? So that's one way. Another way I want you to explore. So far ini faham ke? These 3 steps. Can you relate to the basic of the process, etching litho plus etch? Okay. So bila you guna litho and etch, you can it's not a rigid process. You can combine them in many possible ways in order to realize many different features. Okay. Yeah, they can etch the resist exactly. Okay. So bila you guna litho plus etch, you can use them in many ways in order to get your features. It's not like strictly pattern then etch kat tengah kosong tu. That's it. No, you can do undercut, you can do positive profile depending on apa yang kita nak lah. Kalau if your device requires positive profile like that, or your device might require undercut or something like curved in macam Amirul draw tadi tu, so that can be done as well. So you just have to use the right litho details, parameters, and the right type of etching in order to realize your features. So it's not necessary to say it's not right to say undercut is bad, because in some cases you might need undercut. Okay, so in some other cases, if you're talking about CMOS, then undercut is bad generally ya, sebab you tak nak undercut. Tapi mungkin ada device yang you nak undercut, you nak macam tu, dia punya features nak macam tu kan. So then you have to use undercut and isotropic to some extent. Okay. So those are the things. You can combine litho and etch in many different ways in order to get your features. So that's the essence that I want you to get from this litho plus etch topic. Okay. So I want you to explore another one that's called double patterning technique. Double patterning litho lah, ataupun double patterning technique. Sama je. This can be done as well. So last 2 batches, I think when I discussed the very same question, one student proposed double patterning. Maksudnya you buat, sorry, saya pergi reply dekat Faris pula. I should have written to everyone. Hold on. Okay, double patterning lithography or double patterning technique. That means you can, in fact, this is being used in the current technology, in the state of the art technology, advanced technology. That means you pattern sekali 200 nanometer and then you repattern second time. Maknanya resist yang masih ada, okay, you pattern first time 200 for example, and then second time you pattern, you shift the mask. So that you remove the half portion of the resist daripada 200 tu. Maksudnya you pattern sekali you dapat litho punya pattern kan, 200 CD, 200 nanometer. Kemudian you repeat the very same CED process, you tak etch lagi. Habis CED pertama, you go for another CED, but then you shift the pattern dekat chrome dengan glass punya area tu, transparent dengan opaque area tu, you shift supaya you expose the light, assuming positive resist, you expose the light on the resist yang 200 tu, tapi you ambil half je, you expose on the half of the resist. So bila you expose on the half of the resist, out of 200 you expose the half part je, 100. So then when you go to develop, you can develop this half. Kan? When you develop this half, you're going to be left with 100 eventually, but that requires 2 masking step or 2 patterning. So we call that double patterning lithography or double patterning technique. Faham tak? Can you imagine that? Please confirm.
Oh, faham.
You pattern 2 kali lah, maknanya kita boleh buat 200 ya. So 100 tak mampu. So kita buat 200 dulu. Kemudian you habis CED, jangan etch lagi. Sebab kita nak etch resist nanti kan. So jangan etch sebab kita nak pattern the resist yang sama tu. Tapi kita nak develop half of the resist now. CED sekali lagi. Tapi you don't have to code in this case. You don't have to code because the resist is already there. So maknanya you C tu is remove lah from the CED. You expose saja and develop. You expose structure yang saya lukis lah, mungkin some of you tak dapat. Ada yang tak dapat ke? Saya share whiteboard lah. Dah 9.40 lah.
Tak dapat.
Saya lukis kat sini so that you can. Sekejap tengah buka whiteboard. Okay, let me share the screen. Whiteboard. Okay, can you see the whiteboard on the screen? Nampak whiteboard kosong?
Nampak?
Right, cool. Okay, so kita buat first first CED lah. I'll just put it first CED. Then you end up with resist. Saya buat resist on silicon ya to simplify supaya kita resist PR. Done. Your first CED is done. You get 200 nanometer of printed resist during the first CED. Okay. So next, lari pula. Okay, next you go for the second CED. Second CED, but then you don't have to do the C. You just expose and develop. That's why creativity comes in. You don't have to really go through a rigid CED process. Resist yang sama ni 200 nanometer, right? So when you expose, katalah ni reticle kat atas, reticle ni opaque area, light cannot pass through, and this portion is the transparent area, so light can pass through, and this is positive resist. So apa jadi kalau positive resist? Exposed area, what happens? What happens to the positive resist when exposed? Soluble, right? Soluble. So you expose, that means bila you bawa CD, you run the second time CD, you shift the mass so that it's exposing 100 nanometer of the 200 nanometer. So you end up during development, so this one during exposure, there'll be activation, those to clear and all those stuff. Dia akan jadi soluble, so photo solubility, blah, blah, blah. So then you develop, you will be left with 100. You akan tinggal 100 lah after the development process. So there you have your 100 nanometer of your intended resist. But this requires two masking step. Two masking step means 2 kali litho lah. So misalnya you akan dengar bila you fabricate MOSFET or whatever, this process requires 40 mask, 50 mask, 60 mask. Maksudnya 60 kali lithography untuk siapkan chip tu. Daripada first step sampai hujung, you require 60 masking step. Litho, process etch, implant, blah, blah, blah. Mai balik litho. It will come back in cycle. Okay, in cycle. So that means you require altogether 50, 60 masks. So in this case, to realize this double patterning, you can, since your system is only capable of 200 nanometer, you can buat 2 kali lah masking. Okay, 2 kali masking kalau kita nak pakai RIE, ISO plus anisotropic macam jawapan tadi tu. So you can just do double patterning to shift the position of the mask so that you expose half part of the 200 and half part becomes soluble, and you'll be left with another half of the resist. And there you go, you have your 100 nanometer. So is it okay? Is it clear? Double patterning? Right? Clear? Cool. Right. Good. Yeah. 11:45. Let me just go to the slide for the diffusion for the next few minutes. So clear. So sekarang you know how to combine. It can be done by isotropic plus anisotropic macam tadi tu, dan also double patterning. Etching. So stop sharing, discard. Diffusion. Okay, let me go to diffusion briefly. Jari bulan. Wait, kenapa tak boleh buka ni? Oh, okay. Just have to open. Discard this one first. Okay, diffusion. Okay, can you see the slides on the screen? Diffusion. Okay, good. So let's just go through briefly. Diffusion. So it is the process that we need to do in order to dope certain regions or blanket kita dah discuss malam semua, the whole surface ataupun in certain areas we nak dope with N type or N plus or P type or P plus P type or P plus, or in fact P plus plus, N plus plus, localized or blanket. Okay, so the process that we need to use in order to realize this, you need to diffuse. You need to diffuse the dopants, like say phosphorus, arsenic, antimony for N type, assuming silicon is the host, or boron or gallium or aluminium into silicon to make it p-type. Okay, so the process is called diffusion. We also have another process that we're going to discuss after this process. It's called ion implantation. Satu proses ni kita diffuse. Kita diffuse means you send the atoms of phosphorus or whatnot into the silicon. Dia akan diffuse masuk dalam silicon. We learn about diffusivity during 386. Okay, you can calculate diffusivity and all those stuff. So you can, bila atom diffuse into silicon at certain diffusion rate, you can then create a junction. Okay, junction. Kalau you punya wafer is like p-type, then if you diffuse phosphorus with certain diffusivity punya properties, and then you can design your junction depth. Okay, junction depth. So the key word here is junction depth. You want to create a PN junction, but then how deep is your junction? How deep is the diffusion depth that you want to have? So that's called PN junction punya depth lah, ataupun kita panggil junction depth in this case. Okay. In the other process, ion implantation yang kita akan belajar selepas ni, you can implant at high energy. Maknanya you use phosphorus or antimony or arsenic, you implant, you tanam, you bombard at high energy. Maknanya dia akan strike the silicon at high energy, then you can in fact embed the atom tu, phosphorus ke arsenic ke antimony ke, at certain depth, specific depth, into the silicon. Maknanya you can in fact tak ada apa-apa dekat surface, tapi you ada some phosphorus dekat dalam, because you can bombard the atoms at high energy, and macam tanam dia lah, impact dia terlalu tinggi, then you can embed the atom at certain position within the depth of silicon. But for diffusion, you diffuse. That means along the way atom to diffuse, dia akan jadi N type lah. Tapi untuk implantation, you can send at certain specific depth, tapi atas dia tak ada apa-apa. Okay, so that's the main difference. So let's just go through briefly. Yeah, I'll just skip this. Okay, RCA tadi saya dah upload RCA video of UNSW on eLearn. You can see how is it carried out. In isotropic and isotropic kita discuss. So impurity diffusion, fundamental process step in microelectronic fabrication. So we diffuse, or we incorporate diffusivity, incorporate atoms, because you want to control type of majority carriers. So if you relate to what we learned in 386, we learn about majority carriers, we learn about minority carriers, we learn about N times P equal Ni squared, law of mass action. You learn about the role of majority carriers and the role of minority carriers in certain devices, right? So when you control the majority carriers, you're actually controlling the resistivity, or some condition we say sheet resistance of the dope layer. Okay, so for example, if you look at MOSFET, for example, say this is your gate, okay, polysilicon macam kita discuss tadi, and then you have your gate oxide, and then you have your N-type silicon as your substrate. Then to be able to have this source and drain P-type on both sides, you need to do doping. Okay, macam mana nak doping? You can do implantation that we're going to discuss later on. And you can also do diffusion. So that means in this case, to be able to realize this P-type source drain on the sides of the gate, you need to diffuse a certain depth of P-type. In this case, say boron. Okay, you have to diffuse boron into this brown or red regions, okay, in order to have your p-type. And then when you talk about your p-type dopants here, we're talking about how high is the doping level, and then how deep is the junction. Deep of the junction ni maksudnya your depth of this p-type. Okay, maksudnya how deep is this? That's called junction depth. Junction depth. Kita akan belajar nanti cara nak kira junction depth in this topic. And we call it XJ, junction depth. So how deep you want to go, or how high is the doping level? Doping level, is it 10, 16, is it 17, is it 18, is it 19, is it degenerate? Okay, so that can be designed by diffusion process. All right, every semiconductor depends on the ability to fabricate well-controlled, locally doped. Okay, so remember when you do diffusion, it can be either locally doped, certain region yang you nak dope macam tadi, source drain, or it can also be blanket. Blanket means you nak dope semua surface to p-type, then sitting on n-type. Okay, blanket. So it can be localized, or it can be blanket. When impurities are introduced, it will change the electrical properties of the semiconductor, as what we learned during doping last time. Kita nak alter conductivity and inversely resistivity. Okay, so when you talk about doping a wafer, so katalah you ada wafer kat sini, from the side, let's put it vertical. So kita nak dope dekat atas ni, for example, you nak dope atas ni, a very thin layer of phosphorus, for example. Katalah you punya wafer ni p-type. So to be able to fabricate a p-n junction, you need to diffuse a phosphorus to make it n-type. N-type. Katalah kita pakai phosphorus. To be able to know the depth of the junction, okay, kita akan pakai this graph. Kita akan discuss in detail later on. So say your wafer has a doping level of 10-15. Tengok kat sini. So this is the doping level of your wafer, bulk concentration ni. So that means your wafer has 10-15 of doping level. So where do we get the 10-15? Kat mana kita dapat doping level in the wafer of 10-15? In which process did we incorporate this 10-15? Let's recall our previous process. Kat mana kita dope wafer tu? Recall the very early step of this course. Where did we dope the wafer? Sebelum kita buat junction ke atas je. Where? Which process? Anyone? Couple of weeks back, where did we dope the wafer? When did we dope the wafer? Kenapa tiba-tiba dia ada 10-15 or 10-16? When? Let's finish in like 5 minutes. Come on. Any answer? Anyone? Kat mana kita dope wafer? Bila kita dope dia? Amiro, bila kita dope dia? Tak ingat. Tak ingat. Kat mana kita dope dia? How did you get the wafer in the first place? Where do you dope the wafer? How did you dope the wafer? Hadi, ingat Hadi? Bila kita dope Hadi? How come you have 10-15 suddenly? Or 10-16 perhaps? Or 10-17 perhaps? In the wafer? Come on. Senangnya soalan ini. Bila kita dope? Recall your wafer processing last time? Yes, exactly, molten. So apa proses tu, Haziq? When we melt the silicon and form solidified ingot, what is the name of the process? Float zone is the refined version, yes. FZ is one process. What is the other one before float zone? The most common one. Float zone is a bit more refined, that means higher quality. Yeah, Czochralski, yeah, Czochralski process. CZ lah, kita panggil CZ, tapi Czochralski, that's how you pronounce it. Czochralski, yeah. So learn how to heja dia. Czochralski process. So that's when you incorporate boron of 10-15 into the melt. Remember kita discuss tentang dopant segregation, okay? In the liquid over in the solid, right? In the solid over in the liquid, right? So 0.8, 0.35, all the stuff for boron, phosphorus, respectively. So that's when you incorporated your dopant into the silicon. Sekarang dopant dah ada dalam silicon. Kita dah proses polymer tu. All the way up to this level, diffusion. So now your wafer has 10 to the 15 incorporated from your Czochralski process, for example. Then you diffuse a very thin layer of phosphorus to make it N-type so that you end up with a PN junction on the surface, N-type sitting on P-type, PN junction. So the dopant profile that you will get will follow this kind of profile. Bila you dah diffuse, the phosphorus will take this profile more or less, depending on our model, our assumption, our process details. Dia akan, ni zero ni will be your zero here. X0 ni will be surface of the silicon. Okay, dia akan diffuse into silicon. Dia bukan sit on silicon. Dia akan duduk dekat silicon. Atas surface silicon tu lah will be N-type. So silicon will be consumed during the process. Then it will go, the profile will go into the silicon. Maksudnya into the silicon, masuk dalam silicon. So the junction depth in this case, how do we determine? The junction depth will be the intersection between your profile and your bulk concentration. Okay, almost done. Your profile intercept dengan your bulk concentration at this point, right? There. So bulk is here, intersection point is here. So in this case, if you put it down here, sampai ke x-axis, you can see that the junction depth here is about 1.5 micron, more or less. So your xj of this process will be 1.5 micron. So that means if you say your wafer is here, so 1.5 micron, the first 1.5 micron of the silicon wafer will be N-type now after the diffusion process. And then the remaining, say 200 micron, 200 minus 1.5 will be the P-type. P-type can remain as 200 minus 1.5. And then 1.5 will be a very thin layer of N-type forming PN junction after the diffusion process. Okay. So nanti kita akan continue Friday on the remaining parts in the diffusion process. So is it clear so far? Diffusion, recall the P-type doping in the Czochralski, and then your junction depth determination more or less. Is it okay? Clear? So junction depth will be the intersection between your profile and your bulk concentration. Tak kira lah P-type ke N-type ke, tapi kalau bulk N-type, then your profile will be P-type. Kalau bulk P-type, your profile will be N-type. But the intersection between those two curves, those two lines, and then extrapolated to x-axis, you can get your junction depth. And this case is about 1.5 micron. Right, so any question? Ada? So if there is no question, then I'll see you on Friday, inshallah. All right, then, bye-bye. Thank you, and assalamualaikum. Stay safe.